Every second, billions of packets travel across the internet. Some carry your bank transaction, some stream your favorite videos, while others keep you connected in online games and video calls. But have you ever wondered why a file download waits until every single packet arrives correctly, while an online games can continue smoothly even if a few packets are lost? The answer lies in two transport layer protocols, that is TCP and UDP. In this video, we will go beyond the basics. You will learn how TCP and UDP actually work, why modern applications choose one over the other, and we will even capture and analyze real packets using Wireshark so you can see everything happening behind the scenes. So let's dive in and uncover what really powers communication on the internet. TCP or Transmission Control Protocol is one of the core protocols of the internet, and its primary responsibility is to provide reliable end-to-end communication between the application running on different devices. Imagine you are sending an important document to a client. You wouldn't simply throw the document into the mail and hope it reaches the destination. Instead, you would want confirmation that it was delivered completely in the correct order and without any missing pages. That's exactly what TCP does. Before any data is exchanged, TCP first establishes a connection between the sender and the receiver. This process is known as the three-way handshake, which we will explore in detail later in this video. Once the connection is established, TCP breaks the data into smaller units called segments. Each segment is assigned a sequence number, allowing the receiver to identify the correct order of the data. As the receiver successfully receives these segments, it sends back an acknowledgement or SCK packet, confirming their arrival. If a segment is lost or corrupted during transmission, TCP detects the problem and automatically retransmits the missing data. Because of these mechanisms, TCP guarantees that data reaches its destination accurately, completely, and in the correct order. Of course, all these reliability features come at a cost. Establishing connections, waiting for acknowledgements, and retransmitted lost packets introduce additional overhead, making TCP slightly slower than the UDP. However, for applications where data integrity is more important than speed, such as web browsing, online banking, email, file transfer, and software download, TCP is the preferred choice. So in simple terms, TCP prioritizes accuracy over speed, making it the protocol we trust whenever losing data is not an option. Now let's take a look at the TCP header. Every TCP segments begin with this header before the actual data. It contains all the information required to establish a connection, deliver data reliably, and ensure communication between applications. At the top, we have the source port number and destination port number. This identifies which application is sending the data and which application should receive it. Next is the sequence number, which keeps track of the order of the data. This allows the receiver to reassemble all the segments correctly. Right below it is the acknowledgement number. It lets the sender know which data has been received successfully and what the receiver expects next. The data offset indicates the size of the TCP header, while the reserved field is kept for the future use. Next, we have the flags. For an example, SYN is used to establish a connection, SCK acknowledges received data, and FIN is used to terminate the connection. The window size is used for flow control, telling the sender how much data can be transmitted before waiting for an acknowledgement. The checksum helps detect errors during transmission, ensuring the data hasn't been corrupted. The urgent pointer is used to mark urgent data, although it's rarely used in modern networks. Finally, the option field provides additional features such as maximum segment size and window scaling to improve TCP performance. Together, all of these fields make TCP a reliable, connection-oriented protocol capable of delivering data accurately and in the correct order. One of the key characteristics of TCP is that it is connection-oriented protocol. This means that before any actual data is transmitted, a connection must be first established between the client and the server. This process is known as TCP Three-Way Handshake. To better understand this, imagine you are making a phone call to a friend. Before you start your conversation, you first need to make sure the other person is available and ready to talk. The TCP Three-Way Handshake works in a very similar way. In the first step, client sends a sync or synchronized packet to a server. This is like calling your friend and saying, "Hello, I would like to talk." Along with the request, the client also sends its initial sequence number. After receiving the request, the server responds with a sync ACK packet. This is equivalent to your friend answering the call and saying, "Hello, I can hear you and I am ready to talk." Here the server acknowledges the client request while also sending its own initial sequence number. Finally, the client sends an ACK or acknowledgement packet back to the server. This is like replying, "Great, I can hear you, let's begin our conversation." At this point, the three-way handshake is complete, and the connection between the client and the server has been successfully established. Only after this process does TCP begin transmitting the actual application data. This handshake ensures that both devices are synchronized, ready to communicate, and aware of each other's initial sequence number. As a result, TCP can provide reliable, ordered, and error-checked communication through the entire session. UDP or User Datagram Protocol is another transport layer protocol used on the internet. Unlike TCP, its primary responsibility is to deliver data as quickly as possible without establishing our connection beforehand. Imagine you are listening to a live sports commentary on the radio. If you miss a few words because of a weak signal, the commentator doesn't stop and repeat everything from the beginning. Instead, they continue broadcasting so you can keep up with the live event. That's exactly how UDP works. Instead of establishing a connection before communication begins, UDP simply sends the data directly to the receiver. There is no three-way handshake, no acknowledgements, and no retransmission of the lost packets. Each piece of data called a datagram is sent independently. If a datagram is lost, delayed, and arrives out of the order, UDP does not attempt to recover or rearrange it. It simply continues sending the remaining data. Because UDP eliminates the overhead of the connection establishments, acknowledgements, and retransmission, it is significantly faster and more efficient than TCP. However, this speed comes at the cost of reliability. For applications where low latency is more important than perfect accuracy, such as online gaming, video conferencing, voice calls, live streaming, and DNS queries, UDP is the preferred choice. In these applications, receiving data quickly is often more important than waiting for every lost packet to be recovered. So in simple terms, UDP prioritizes speed over reliability, making it the ideal protocol for real-time applications where fast communication matters more perfectly than data delivery. Now let's take a look at the UDP header. Unlike TCP, the UDP header is much simpler because UDP is designed for speed and low overhead. In fact, the UDP header is only 8 bytes long and contains just 4 fields. At the top, we have the source port number and the destination port number, each occupying 16 bits. These fields identify which application is sending the data and which application should receive it. Next is the length field, which is also 16 bits. It specifies the total size of the UDP datagram, including both the header and the actual data. Beside it is the checksum field. This field is used for error detection. It allows the receiver to verify whether the datagram was corrupted during transmission. However, unlike TCP, UDP does not retransmit lost or corrupted data. Finally, we have the data, also known as the payload. This is the actual information being transmitted, such as DNS query, a voice packet, or a game update. The size of the payload can vary depending on the application. As you can see, the UDP header contains only the essential information required to deliver data. There are no sequence number, acknowledgements, or connection management fields. This simple design keeps the overhead low, making UDP an ideal choice for real-time application where speed is more important than guaranteed delivery. Now that we have understood how TCP and UDP work in theory, let's see what they actually look like on a real network. We will begin with TCP. First of all, I will create a simple web page by typing the following command on the screen. Now, I will start a local web server using Python. Type python 3-m http.server 8080. Our server is now running and waiting for incoming connection. Next, I will open Wireshark. Open new terminal and type sudo wireshark. Since I am communicating with a local web server running on my own machine, I will capture traffic on the loopback interface, yellow. Now let's open a browser and navigate to http://127.0.0.1:8080. The web page loads successfully. If we return to Wireshark, we can already see lots of capture packets. To focus only on the TCP traffic, simply type TCP into the display filter. Now the capture contains only the TCP packets. To make the communication easier to follow, I will right-click one of the packets, choose conversation filter, and then select TCP. This isolates the complete TCP conversation between the browser and the web server. Now let's examine one of these packets more closely. Expanding the transmission control protocol section reveals the TCP header that we discussed earlier. At the top, we have the source port and the destination port, which identify the sending and the receiving applications. Below that is the sequence number, which keeps track of the order of the transmitted data. The acknowledgement number tells the sender which data has already been received successfully. Next are the TCP flags, which control different stages of the connection. The window size is responsible for flow control, indicating how much data the receiver can accept before sending another acknowledgement. Finally, the checksum is used to detect transmission errors. Everything we discussed earlier is now visible inside an actual TCP packet. Now let's look at the most interesting part, the TCP Three-Way Handshake. If we look at the beginning of this conversation, we can clearly identify three packets: SYN, SYNAC, and ACK. Let's examine each one. First packet is the SYN packet. This is sent by the browser because it wants to establish a TCP connection with the web server. Notice that only the SYN flag is enabled. You will also notice the initial sequence number, which Wireshark displays as 0 using relative sequence numbers. TCP will use this sequence number throughout the entire communication. Now let's open the second packet. This is the SYNAC packet sent by the server. Here the server acknowledges the client request while also sending its own initial sequence number. Notice that the acknowledgement number is now 1, indicating that the server has successfully received the client initial sequence number and is expecting the next one. Finally, let's look at the third packet. Here only the ACK flag is set. This packet confirms that the client has received the server response. At this point, the three-way handshake is complete, both devices are synchronized, and TCP is now ready to exchange the actual application data. Now let's compare this with UDP. I will start another packet capture in Wireshark. This time, I will capture traffic on my Ethernet interface. To generate some UDP traffic, I will simply perform a DNS lookup. Type nslookup google.com in your terminal. If we return to Wireshark and filters the packet using UDP, we will immediately notice something different. Unlike TCP, there is no connection establishment. There are no SYN, SYNAC or ACK packets. Instead, UDP simply sends the request immediately. Let's open the DNS query packet and expand the user Datagram Protocol section. Notice that how simpler the UDP header is. It contains only 4 fields: source port, destination port, length, checksum. That's it. There are no sequence number, no acknowledgement numbers, no flags, and no connection management fields. This lightweight header is one of the main reasons UDP is much faster than TCP. If we look at the packet exchange, only 2 packets are involved. The first packet is the DNS request sent by the client. The second packet is the DNS response returned by the server. There is no handshake. Here are no acknowledgements. UDP simply sends the data and waits for the response. And this perfectly summarizes the difference between these two transport protocols. TCP spends a little extra time establishing a connection and verifying every piece of data, making it highly reliable. UDP removes all of this overhead, allowing data to be transmitted with much lower latency. That's why applications like web browsing, file transfers, and online banking rely on TCP, while online gaming, voice calls, video conferencing, and DNS choose UDP for their speed. And that's a complete overview of TCP and UDP. I hope this video helped you understand how this protocol works and why different applications rely on one over the other. If you are still wondering how applications know where to send and receive data, make sure to check out my previous video on port numbers. It perfectly complements what we have covered today and will give you an even deeper understanding of computer networking. If you found this video helpful, don't forget to like, share and subscribe, and turn on the notification bell for more networking and cybersecurity content. Thanks for watching. I will see you in the next video. Until then, enjoy networking.